Hello, Year 12. Welcome to another exciting for you statistics lesson. As we said before, in A-level biology, you need to understand how to interpret the test. I'm not as concerned about how it's carried out. However, I think you should be aware of how you arrive at the actual test statistic. So I'll take you through the process, explain why we use this particular statistical test, and go through the way that we interpret the test statistic. So this is called the student's t-test, and you might wonder, why is there a pint of Guinness on the screen? That's because this particular test was developed by a gentleman called William S. Gossett, also known as Student. He didn't actually give his name to the test. It probably should have been called Gossett's t-test. But he was working for Guinness at the time, and he was tasked with ensuring, or helping to ensure, the quality of the Guinness. Guinness were brewing something like 1 billion pints of Guinness, and they wanted to ensure that the quality was consistent. And so what Gossett managed to achieve was to develop a mathematical test that assessed the quality of the hops in use. He published his work under a pseudonym of Student, because Guinness didn't want any of their competitors to know of the work that he'd been doing, in case they got ideas themselves about how they could ensure quality. So it was kind of published under a pseudonym, and he often kind of goes forgotten, but there are many statisticians that know him rather well. So he developed this particular t-test, which is often the first statistical test that many students are taught about. So let's kind of go through and have a look at the key things for this particular test, and remind you of a few key facts when we're doing any statistical analysis. And the first thing that we always need to do is come up with a null hypothesis. So a bit of knowledge retrieval. Let's see if you can remember how to come up with a null hypothesis. So I'm going to give you 3 statements to have a look at. Pause the screen, have a think. What do you think the null hypothesis will be for these particular examples? Okay, so pause the screen now. Okay, hopefully you got a chance to have a look at that and think about what the null hypotheses would be. So the first one, we've got this idea of increasing light intensity and photosynthesis. So a simple null hypothesis could be that increasing light intensity has no effect on the rate of photosynthesis, or increasing light intensity doesn't increase the rate of photosynthesis, something about that idea of no effect. Increase in smoking and lung cancer development. Again, there is no correlation between increasing in smoking and the development of lung cancer. That would be appropriate. And for the last one, decrease in concentration and rate of reaction. There will be no correlation between a decrease in concentration and the rate of a reaction. So that idea of a hypothesis of no effect or no correlation should be by now fairly straightforward to come up with. Other things we need to do with any statistical test is make sure we've chosen the correct one. There's 3 that we need to be concerned about. We've looked at one of them already when we're now looking at the t-test. And we give reasons why this particular test is chosen. This one is all about comparing means. So it needs to have 2 sample sizes, and we're looking at comparing the mean value between those sample sizes. Okay. The level of statistical significance, 5%. We've referred to that previously. So we're looking at less than 5 times out of 100 was something have occurred purely by chance. That's what we mean by this 5% level of statistical significance. We present our calculations. That's what this presentation is mainly about. And then from those calculations and the result that we generate, we then look at are we going to accept or reject our null hypothesis. So in this particular statistical test, why this is relevant, why the t-test is useful, the samples we're going to look at are independent of each other, so they're not linked in any way. They're 2 independent sample sets. The data we're looking at is what's known as a normal distribution, so it's not skewed in any particular way. There are statistical measurements you can do to determine if something's normally distributed. We're making the assumption in this case that the samples are. We need to have a reasonable sample size. We did Spearman's rank, and we said we need a minimum of 5 values. With the t-test, we need to have a total sample size of at least 15. Okay, at least 15 samples. Okay, so that would make sure that this test is suitable. And this is what we're going to look at. This is the exemplar. again, we're going to keep this kind of from a biological standpoint. In this case, we're investigating some students going to the shoreline, and they're going to investigate a dog whelk. A dog whelk is a small mollusk found on the seashore. They're predatory, believe it or not. They feed on sort of common mussels that you also find on the seashore. They kind of drill through the shell and eat the contents. And some students are investigating the height of the dog whelk, and they're intrigued to find out is the height of the shell related to where you find it. So, for example, on a sheltered shore, are the dog whelks predominantly higher in terms of the height of the shell compared to an exposed shore? There might be some logic in that. If you've got an exposed shore, more likely going to get stronger wave action, stronger winds, more hostile environment, and perhaps having a larger or higher shell height might be disadvantageous. It could be more likely you get knocked off the rocks. So perhaps there is a difference in shell height when you look at sheltered and exposed shores. So we're going to look at some data analysing those particular differences. So in this case, the null hypothesis is relatively straightforward. We're saying there's no difference between the mean shell heights of dog whelks on the exposed and sheltered shores, or exposure of the dog whelks to wave action and a hostile environment has no impact on the shell height. Okay, so straightforward null hypothesis. Now, the formula for the t-test always looks quite daunting for many students. It shouldn't be, but it usually kind of panics a few. And the key thing is just to understand what the different bits relate to. So we're interested in determining this t-value, and that is our test statistic that we can then interpret. So we've got some information at the top where we've got x with the bar running across the top, the x bar value. That is the mean value. And the number 1 means sample set 1, so the first sample of data, the first set of dog whelks from one particular shore, and the mean value for the second set of data for the opposite shore that we're going to look at. And then those values are divided by this S value and this N value. The S is the standard deviation. Okay, now we've looked at standard deviation previously, so you'll need to look back through your notes and remind yourselves how to carry out standard deviation, because you will need to do it. And in this case, we're going to square the standard deviation. If we square the standard deviation, we get a value known as the variance. So in this case, the square of that standard deviation is the variance value. It's the variance value that we're going to be using. To do that, you've got to work out standard deviation first. And n is quite simply just the number in that particular sample. So once you understand what these particular parts of this equation relate to, hopefully it becomes a lot more straightforward to work out. So what you're going to do, we're going to give you some data, and I want you to kind of do some of the processing yourself and then compare it to my data, just so you're kind of going through your own method and your own kind of way of generating that test statistic, and then we'll look at the interpretation. So get a pen and paper ready. This is the data that I'd like you to make a note of. So you can either freeze the screen and just go directly from what I've got, or you can put it into Excel, or you can just make a note of those particular values. So if you pause the screen now, just to make a note of that data. Okay, hopefully you've managed to do that. And this is what I'd like you to do with that information that you've got. Okay, so you've got those values hopefully written down somewhere else at the moment. And what I want you to do is to work out these particular missing values. So for each data set, I want you to work out what the total value is. I'd like you to work out the mean. Okay, so for sample set 1, what are those 2 values? For sample set 2, and then quite simply, what's the difference between the mean? How many samples are there within each data set? Just straightforward. And then looking at the standard deviation. That's a bit more difficult to generate, so go back through your notes, look at how you did that previously. Most people's calculators quite easily generated that value for you. And we're looking for that sigma symbol, sigma n minus 1, because the standard deviation we're looking at is for a sample of the whole. So we're not looking at total standard deviation, we're looking at sample. So we're going to use sigma n minus 1 as our standard deviation measurement. Then we're looking at the square of that value, and you're going to take the variance and divide by n. So hopefully you can complete that table. So if you pause it there and see if you can complete that missing data. Okay, hopefully you've managed to do that. So let's go through and see if you generate those things correctly, compare them to mine, assuming mine's correct, of course. So there's my raw data. Total, quite simply, is to add them together. Okay, so there's the sum for each data sample. So 387.4 for the sheltered shore, that was the heights, and 317.8 for the exposed shore. So it looks at face value that dog whelks on a sheltered shore appear to be higher. If we look at the mean values, again we can see 32.28 mean shell height compared to 26.48. So it does look like there's a difference in the means, but we're looking at, is there a statistical significant difference between those means, or are those means just due to chance? That's what we're going to try and look at. Okay. Next step's fairly straightforward. So we want the difference between the two mean values. Okay, that comes out nice and easy, 5.8. We'll look at those two. N, you're just counting how many values there are. So there's 12 for each, so there's a total of 24 in the whole data set. And the standard deviation for each one, if you managed to do that successfully, hopefully you generated those two figures. So it looks like for the sheltered shore, it's got a larger standard deviation. That would suggest that there is a greater variety of data and a greater spread around the mean. So a wider variety within that particular sample set, and a smaller spread around the mean for the exposed shore, so more of them are closer to that mean value. Variance is just the square of that particular value, and then we've got variance divided by the number within the sample, and that gives us those two numbers. So once we've generated those, the next step is quite simply substituting those into the t-statistic equation. Which I'll remind you here, again, this isn't something you need to memorize. You wouldn't be asked to do this in an exam, but it's useful to go through the process just to see how that particular t-value is generated. Okay, so if you've managed to complete that table, you've done most of the legwork. The next part is just substituting those into the equation. So let's take you through it step by step. Big criticism from many students is they tend to try and cut corners. And if you cut corners, invariably you will go wrong somewhere, and there'll be some sort of error that you put in. So go through this step by step. Try not to cut any corners. So what we're going to do first of all is substitute into the equation the values that we know. Okay, so in this case the t is 32.28 minus 26.48. I'm rounding these values at this stage just to kind of keep my information on the screen simple. In reality, when I've worked this out, I've kept the total value, the 32.283333. I don't want to bring in any errors by rounding normally, so I've just rounded just to keep this display simple in this case. But I've got 1.064. Again, I've rounded that one temporarily on the screen at 0.422. So I'm putting everything in that I know that I've worked out. I'm then going to simplify that slightly. Okay, to give 5.8 divided by the square root of 1.49. It's 5.8 divided by 1.219, and then I get my test statistic. Okay, 4.758. That's the value that I'm interested in. So the next bit is usually the part that most students find quite confusing as to what do we do with that particular value, because it's unusual compared to what we've done previously when we looked at Spearman's rank. Okay, so 4.758 is the value of choice, and we now need to interpret that. So there's kind of a number of steps involved in this particular statistical analysis. We've done the first one, and we've calculated the t-value. The next thing we need to do is do something called calculate the number of degrees of freedom for the two samples. I'm going to come back to that bit in a moment. That's the part that usually confuses a few people. It is a statistical term, this idea of degrees of freedom. I'll try and explain that as best I can shortly, but it's nothing you need to concern yourselves too much. Anyone that goes on to be a statistician, you might go into it in much more detail than we need to, but I will try and give you an idea of why we have this idea of degrees of freedom. Once we've done that, that will help us look up what's known as our critical value, the same as we did with Spearman's rank. We can then compare our calculated t-value to the critical value, and as we've done before, just decide, is our value greater than or equal to the critical value, or is it less than the critical value? And depending which one it is, we either would accept our null hypothesis or we would reject our null hypothesis. Now, for this particular statistical test, when we're determining the number of degrees of freedom, this is quite simple. The number of degrees of freedom is the total number that we've got across all the samples. So in this case, we had a total of 24, okay, and we subtract 2 from that total. So it's the total number of samples minus 2. So in this case, the degrees of freedom is going to be 22. And I'll now try and explain exactly what we mean by that idea of the degrees of freedom. Okay, and this is the bit that some people might find a little bit confusing. Okay, so what are degrees of freedom? The definition for degrees of freedom is the number of values in the final calculation that are free to vary. Now, that means nothing to most people, so I'll try and run that by doing a little bit of football analogy. So let's assume you were out playing football with some friends and you were trying to come up with who was going to play in which particular position. So there's 11 of you playing and you were going to assign each person a particular role in the team. So initially you've got 11 players to choose from. So you're going to choose someone who's going to be the goalkeeper. Okay, nice and easy. So you could have chosen any one of the 11. You pick one of them out, you now have the goalkeeper. You've still got 10 people left to pick from. So you're going to choose your left back. Okay, so left back's in position. You're going to choose 2 centre halves because you're playing 4-4-2. Then you're going to choose a right back. Okay, again, at the moment, you could have chosen anyone from that was left. Okay, so I've now got 6 players left and 6 positions to fill. So I'm going to choose someone to play on the left wing. Okay, and I've still got a choice who I pick from, so I've got a freedom of choice. Okay, so my degrees of freedom is still, I've got a freedom of choice who I will pick. So I'm going to pick someone for the right wing. I'm going to pick someone to play central midfield. Okay, at the moment I'm left with 2 people. I've still got choice who I'm going to pick. I'm going to play one who's going to be my lead striker, my number 9 up front. Okay, and then I've got 1 person left. I have no choice now. The 1 person left has to be the other striker. I no longer have a freedom of choice. So for every other position, I had a freedom to choose which individual would be involved in that particular position. But for the very last one, I don't have freedom of choice. So in the statistical calculation, this idea of degrees of freedom takes that into account where you're lacking freedom of choice when you're looking at the statistical analysis. Okay, so that's the best analogy I could come up with. Don't concern yourselves too much. If you want to go on and do statistics at a further level, you'll go into it in much more detail and probably end up with a much better explanation than I've tried to give you. But that's just the idea of what we mean by degrees of freedom. So in this case, we had 24 samples. So degrees of freedom, we have 1 less for each data set that we had. So we had 12 in sample set 1, 12 in sample set 2. So we've got 1 degree of freedom for each sample set. That's how we take our degrees of freedom and subtract 2. So we've got a degrees of freedom value of 22. So here's a kind of quick snapshot at a statistical table for the t-test, if I can get my words out. We're interested in the 5% level, as always. Okay, so less than 5 times out of 100 was something that occurred by chance. So in this case, the differences in the means occurred by chance. And we need to find the degrees of freedom that equates to 22. Okay, so we're looking at degrees of freedom level, and we're going to find where those 2 values come together, the 5% level and the 22 degrees of freedom. When we do that, we find this particular value down here. Okay, so let's quickly zoom into that. So our particular t-test statistical value that we look up is 2.074. We calculated a different value to that. All we've now got to do is compare the 2. Okay. So our test statistic was 4.758, and that is greater than the critical value when we look it up at 2.074, and therefore because of that we reject the null hypothesis. So we did Spearman's rank earlier. It was the same kind of idea. If our value was greater than or equal to the critical value, we would reject the null hypothesis. There is a less than 5% probability, or less than 5 times out of 100, would the differences in the mean shell heights occur due to chance. Okay, so if you notice that the interpretation phrase is almost identical to what we looked at when we did Spearman's rank. The key phrasing that's different is this particular statistical test looked at the differences in the means, so our interpretation needs to be referred to the differences in the means. There's a less than 5% probability that the difference in the means and the shell heights was due to chance. Okay, and here's a standard way of looking at that information. So if our calculated value of t, so the t value that we've worked out, is greater than or equal to the critical value of t, that's the value that you look up in the lookup table, then there is a less than 5% probability, less than 5 times out of 100, would the differences in the means be due to chance. And therefore, in this case, we would reject our null hypothesis. So we're basically saying it's not the case that there isn't a relationship. We're saying there probably is a relationship between, in this case, the exposed shore and the sheltered shore does appear to have an impact on shell height. But what if our value had been less than the critical value? Really simple, we're just changing a couple of words in our interpretation. So if our calculated value is lower than the critical value of t, there's a greater than 5% probability that the differences in the means are due to chance, and therefore we would accept our null hypothesis. So the interpretations are very similar to Spearman's rank. Okay, we'll just look at our particular calculated value, compare that to the critical value in the lookup table, and then interpret that appropriately. Hope you find that okay. There'll be some follow-up questions to work through, a few examples to do, and if you've got any problems, just drop me an email, and I look forward to seeing you next time. Bye for now.